Welcome back to R for Economics. In this video, we're going to be going over the Lasso Regression. And this is a regularization or shrinkage approach. And this is where you have lots of regressors and you want to reduce that down to a smaller set. So the GLM net is the package. And we're going to bring in the library. Now, for this, we're going to have a training and a testing in order to show this this approach. So we're going to have training using 100 observations and the testing using 25 observations. The number of regressors that are available, we're going to say is 75. So we have 75 potential candidates for regressors. Now, with 100 observations, this is going to greatly restrict the number of parameters and the degrees of freedom. So we want to bring this down to a much more reasonable number. So let's set up a regression. So we have the errors, which is just drawn from the standard normal, and x's, which we're going to draw from the standard normal, and we're going to have 100 observations, and we're going to have 75 regressors. Similarly, for the testing period, we're going to have 25 observations of the errors, and then 25 by 75 regressors. Our parameters, so how these things are related, we're going to use a functional form and a cutoff, which says that only the first 5 coefficients are non-zero. And we can plot this and we can see that after on the 6th one, so these are decreasing and then they go down to 0. So this is a fixed line where it drops. So now we can generate our model, and we know that we're going to have non-zero parameters for the first ones and then zeros for all the other ones, even though we have 75 regressors. So we can generate our training and our testing periods series. And if this was OLS, we'd just regress Y on X, and we can get a summary of this, and we can see that we get lots and lots of observations. The first 2 or 3, 3 are actually significant, but we know that we should have 5 based on what we see in the graph here. So we should actually be 1 through 5. So all these covariables, the 6 through 75, might be interfering with our ability to get that back. So we're going to use the GLM net approach, which is X and Y, and we're going to say alpha equals 1, which means that it's going to do a lasso, and the family of distribution is going to be Gaussian. So we do our lasso, and we can see what we've printed. We've got a lot of deviations and lambdas, and we're going to plot our regression. And this shows that the first 5 seem to have a significant difference from the remaining ones, where this is kind of saying that, well, the amount of error and stabilization is out here, and these things are remaining fairly small. So if we use the CV, so the cross-validated GLM net, this will give us an idea of how many regressors we should be keeping. And it seems to want to keep somewhere around 9. So we can see that the first 5, V1 through V5, are significant. And then it's saying that some of these other ones seem to have an interaction with the variable. And these are more by accident than anything else. Okay. Now we know what the optimization, the lambda is. That's related to this graph that we see over here. The optimized lambda is out here, and this can give us our optimized form of our model and our optimized coefficients. So once we have that optimized set, we can now estimate our data based on x0, and we can get the mean squared error of our estimates. We can see that it's 1.12. And we can see that the optimized one is much smaller because it's optimizing the based on this model. So our mean squared predicted error is much smaller. If we want to compare these, OLS Optim. What did I forget to do to these? If we want to compare all these, we can see that OLS has the highest predicted error, the Lasso, the native one, and then using the cross-validation optimizes it and gets our mean squared predicted error the smallest. Okay, and if we want to look at the coefficients, we can observe what the coefficients are, and we can see that the optimized one is probably the closest to our actual model. Our cross-validation coefficients are some of our coefficients. And you can see that the restriction that we put on it, the Lasso restriction, is actually forcing the coefficient values to drop. Okay. And these are the true value is the first one. True values are at 7.7. And you can see that the Lasso and the optimized Lasso are much closer to 7 than our OLS, which is at 9 point something. Okay. And we can see how many regressors we have. 5 is the true. OLS is 76. 9 is the Lasso, and then the cross-validation optimized one is closer to 17, which is what we see in the graph over to the right. Great. Thank you, and we'll see you in the next video.